So here's a quick overview or lesson on 3.1 Precalculus. We're going to talk about exponential and logistic functions. By the time this lesson is done, you should be able to evaluate exponential expressions and identify and graph exponential and logistic functions. You should pause this video and write down our definition of an exponential function. An exponential function comes in the form of f of x equals a times b raised to the x. So you notice that's different from your power function, as the variable is the exponent instead of the base. So make note, a must be non-zero, b must be positive, and b can't equal 1. The constant a, we call that the initial value of the function. In other words, that a value is the value you will have when x equals 0. That's why we call it the initial value, kind of like the starting value. And b is considered the base, as I mentioned. So it's important to note that a is the initial value and what that means, because it's going to help you solve problems. If you know the coordinate point when x equals 0, then you actually know the initial value without doing any work. So you're going to use that information on this first problem. In this first example, you're to determine formulas for the exponential function g and h, whose values are given in the table. So you're told that g of x is an exponential function. You're told h of x is an exponential function. With the given information, you should be able to write out what the function actually is. What you're going to focus on is the 0 values and the value when x is 0, or the initial value, and the value when x is 1. If you have those values, the problems are quite easy to do. So we'll focus on the function g first, or g of x. It's exponential. We're given that, so we know it can be written in the form g of x equals a times b to the x. We are given that x equals 0, or when x equals 0, y is 4. Well, that tells us the initial value. That tells us that g of 0 equals 4, which means our a value is 4. Since we already know the a value is 4, we can plug that in for a. Now, we know g of x equals 4 times some number raised to the x. Well, now you just need to take another value. It's really nice when you're given x equals 1, because anything raised to the first power is itself. So we're going to plug a 1 in for x and solve for b. Since we know when x equals 1, y, or g of x, is 12, we can quite easily find that b value. So what we just did there on that line was, when g of x is 12, we have 4b, divide by 4 on both sides, and you get b equals 3. Then you can just write your statement out. So the exponential function that goes with the data provided in these two columns is 4 times 3 to the x. That's the exponential function. So now you try it for h of x. You should pause right now and try that. So you know it's a power function. I'm sorry, an exponential function. So it's going to be in that form. Again, you're given the function equals 8 when you plug in 0 for x. So you know the initial value. You also know the value when x is 1. So plug in those values, and you got b to be 1/4, I'm sure. So there's your exponential function that goes with the data in that third column. So this function matches up with this data here. Piece of cake. So now we'll talk about exponential growth and decay. If you haven't done so already, you should pause this video and write down this definition of exponential growth and decay. So for any exponential function, again, where f of x equals a times b to the x, and you have any real number x, what this is saying, f of x plus 1 equals b times f of x, that's just saying to get the next number, if you go in 1 unit intervals, you would just have to multiply the previous number by b. Now, if a is greater than 0 and b is greater than 1, so we're talking a here is greater than 0 and b, the number that's being raised to the x, is greater than 1, the function is increasing and is considered an exponential growth function. And then what we do is we call that base the growth factor. If a is greater than 0 again, so this a value is greater than 0 again, but b is less than 1, the function is decreasing. And it's called an exponential decay function. There should be a space right there. So when you're writing your notes, you're going to put a space there, in case you didn't know. And we call that base the decay factor. Now remember, when we're talking about an exponential function, remember back to the beginning, we need b to be positive. Do you remember that? We need b to be positive. So if b needs to be positive, and I'm talking about b being less than 1, really what I'm saying is it's between 0 and 1. It's a fraction, non-negative. Now in this next example, what I'd like you to do is consider f of x equals 2 raised to the x as the basic function that you're comparing to. So I'm going to go through 3 examples here where I want you to tell me how to transform this f of x graph into the graph that we're currently on. So the first question is, and maybe you want to just try to do this right now. Press pause on the screen here and think about what's going to happen to each of these graphs. What you can do is you can graph on your calculator 2 to the x to see what it looks like, and then write down what you think would happen to that graph if you take 2 to the x minus 1, or you take 2 to the negative x, or you take 3 times 2 to the x. Write down each of those. Now I'll just quickly go through what is you should have gotten, because it's the same rules that we went through before. What's happening in part A here? Well, for every x value, you're shifting, or you're subtracting 1 from each x value. What does that do? It shifts our graph to the right, 1 unit. It's going to shift our graph right to 1 unit. What happens when you take each x and multiply it by a negative? That's the next question. Well, you're going to have a reflection going on. Where is that reflection when you do it to each individual x? It's in the y-axis. It's the same as saying, well, whatever I got when x was 1 before, well, now I'm going to get that. Now I'm going to get that when x is negative 1. Whatever the y value was for 2, well, now I have that y value is now at negative 2, and so on. And the last one, what happens when you multiply by 3, multiply the entire function by 3, you get a vertical stretch by a factor of 3, or a vertical change, if you will. So the next thing I'll talk to you about is the number e a little bit. You all probably know that e represents a number. It's approximately 2.718. That's all I remember right now. I think maybe 2.1 after that. But a little bit more, maybe you didn't know. Mathematician Euler is the person who first introduced this notation. He used his the first letter of his last name. Is an E. That's why we use the E today. He started using this. The number e can be obtained if you take the limit as x approaches infinity of the function 1 plus 1 over x raised to the x. So that's good information. That's interesting. A little history there for you. Well, e is mainly used or used quite often with exponential functions. We can take the exponential function a times, a times b to the x, and that can be rewritten as a times e to the k times x, where k is some constant. K is some real number constant, and furthermore, if a is greater than 0 and k is greater than 0 for this function, it's an exponential growth function, like we just previously talked about. And if a is greater than 0 and k is less than 0, it's an exponential decay function. I have that written here also, and then you can also see the graphs that correspond with those. What's nice about that is now when you're using e for your exponential function, now you're focusing on if k is here we go, the exponential growth function here, k greater than 0, so k is positive. Decay function is less than 0, so it'll be negative. These give you a good visual of each of those. Feel free to pause again, of course, and copy that down. And now just a few more examples of reflecting, or I mean transforming an exponential function. Now we're going to use e involved with that exponential function, where e is the base. So why don't you pause and go through how the basic function e raised to the x would be transformed if it became e to the x plus 2, negative e to the x, e to the x minus 1. Pause now and do that. Here are the answers that you should have got. E to the x plus 2 is going to be shifted 2 units to the left. Negative e to the x, well, you're negating the entire function, so you're going to reflect in the x-axis. And e to the x minus 1, you're subtracting 1 from the entire function, so that should be shifted down 1.